Welcome back to snt-networks. In today's video, we'll be talking about another part of our series, engineer interview questions and answers, right? Basics to advanced series where we are discussing medium level questions, right? So now this is not about troubleshooting. Mostly, it is mostly about your understanding of protocols. Okay. So let's start with without wasting time. Let's start with the first question. How would you troubleshoot a problem where packets are being fragmented too often? And what layers would you inspect? So this is again an interview question where they'll ask you if you're sending packets from A to B, right? And you see packets are being fragmented. You send packets, but they are being fragmented too often. Now, how do you check, right? What layer would you check? So actually, see, fragmentation happens on layer 3, okay? And segmentation happens on layer 4. So basically, when you're coming from layer 4 to layer 3, it is happening, right? So what impacts fragmentation? MTU. Which layer does it belong to? It belongs to layer 3. So if the MTU is, maximum transmission unit that you have is less than the size of the packet that you're trying to send, right? So, and it will also check MTU along the route. So first you have to check MTU on layer 3, okay? And then you will also check basically MSS on layer 4, or basically your application, to check if basically some protocols like TCP basically can adjust segment size, right, during the connection establishment according to the protocol. So you need to check these two. And basically if there's too much fragmentation and you see because of fragmentation you're getting issues while connection or while sending a chunk of data, then you can choose to reduce the basically MTU size of your interface just to make sure fragmentation does not happen much. Okay, that is the way you can avoid too much fragmentation. Okay, and that is why we have TCP slow start, by the way, guys. So again, an important thing that I shared, TCP slow start helps you maintain the optimum MTU for the whole transmission, including along the way MTU, to make sure that you have optimal MTU, which increases your throughput. Basically, you get maximum throughput. So I hope first question is clear. You will check basically layer 3 and layer 4 just to check, just to make sure it's correct. Now, second, describe how NAT, network address translation, operates at the network layer and its impact on end-to-end connectivity. Okay, so basically, in this question, they want to know, they are trying to ask you how exactly does NAT works. So NAT, or you can say that NAT translate your private IP address. So considering you're here in an internal network, this is your router, this is the internet. So in here you're on 192 series, but here the IP address will be around 10 something XXX, right? Some internet IP address. So when your packet goes out, it cannot take your private IP address. It takes your public IP address. Right here you have source NAT. Since your source IP is being translated, if you're trying to reach something, destination IP will anyway be the same. For example, if you're trying to reach a server, it has 1.1.1.1. For example, the destination will be 1.1.1.1, but your source IP address will change. What will it change to? Basically 10 series, right? Whatever this interface IP address is. Okay, so this is called source NAT. Now, where the destination NAT happens, similarly, if you have a gateway here, this is again internet in between. So you're trying to reach 1.1.1.1, but this interface holds that address. So now you translate this router, particularly your gateway, will translate 1.1.1.1 to, for example, 192.160. Okay, this particular 168 something 2.0. So it will translate it. So now this is called destination NAT, because its destination IP address is being changed, because that if that same packet reaches here, it has source address of 1.1.1.1, destination address of, for example, okay, sorry, it holds the source address of, let me rub this off, let me be a bit clear, 10 series, this series, and the destination will become 1.1.1.1. Now you change this 1.1.1.1 to 192.168.2.0 series. Now from the source side you have source NAT, from destination side you have destination NAT. Simple. Okay, when the destination IP is being changed, is destination NAT. If source IP is being changed, source NAT. Right. Now it says, and its impact on end-to-end connectivity. Okay, now there are a lot of advantages to NAT, right? But once it is not done properly, right, you can say that if any device in between does not hold NAT, then it can interrupt the connection. Okay, uh, then uh, you can say that you need to make sure the in between devices, all of them allow NATing. Okay, and you can also say that it breaks end-to-end IP connectivity because NAT will modify the IP headers. IP headers that exactly we have seen. Here source address was changed from 192 1.1.1.1. Here destination was changed from 1.1.1.1 to 192 series. So this is how basically your NAT works. I hope this is also clear. Now moving on. The third question is how does the error detection at the data link layer differ from error correction mechanisms? So we have error correction in TCP also, right? How does the data link layer help us with error detection, which is different? So basically, error detection in data link layer, right, are different because it uses things like CRC basically. Now your CRC is cycle redundancy check, or you can check it. You can also say that it does frame check sequence, right? FCS. Now it does it at layer 2 to identify basically corrupted frames. So once it identifies corrupted frame, it will discard it right here. Okay, rather than fixing them. So error detection is different. Error correction happens in TCP, wherein if you get any error, you do retransmission to basically get that packet, right? So, and now I'll tell you the difference. Error detection is done at data link layer, which will discard the packet. Error correction, right, involves techniques like forward error correction, where redundant traffic is added so that receiver can reconstruct the original data. Like I told you, it requires retransmission. Okay. Now, the key difference you can say that error detection requires retransmission. Okay, you can say that higher layer protocols will handle the recovery. For example, TCP, while error connection fixes the error without retransmission. Simple as it is, right? Pretty simple. So this is the only difference. So you can say that if anyone asks you, right, you can just say that it uses FCS to detect the error, right? To check frame by frame and discard them rather than fixing them, basically. Okay, because here you're not maintaining a connection. That happens at layer 4. You do at TCP, right? So now this is different. Now moving on to the fourth question. Explain how the sequence number and acknowledgement number fields work together uh, during a data transfer. So this is again pretty simple. If you need to read about this in detail, we already have a video on TCP. So this is core TCP. You will be able to understand a bit better if you click on the I button. So basically sequence number, just to bring it down a notch, just to understand the basics, sequence number is basically, it indicates the position of your first byte of data, right? Acknowledgement number indicates the next expected byte. So for example, this is A, this is B. I have a sequence number, right? I am sending packets from 1 to 100. So my sequence number right now is 100, right? And acknowledgement number will basically indicate the next expected byte. Okay, now 100 is already there. Now what are we expecting next? So here acknowledgement number will become 101 because we are expecting next sequence number to be 101. So now next sequence number becomes 101. Okay, it's again pretty simple. So how they work together is the sender uses sequence number to track data that it is sent, and the receiver uses acknowledgement number to confirm the receipt. So if you're paying a bill, you need a receipt, right? Just to understand how much you have paid. So this is the receipt basically. If you have paid 100, it will say that 101. If you want to pay, next it should be 101. So this is how the sequence number and acknowledgement number work. Again, very simple. If you know about the TCP handshake, it's again pretty easy. So this was a very small question. I hope this was clear. Now this is good. How does the identification field in the IP header help with packet fragmentation? So there are actually a few fields, right? For example, in the IP header, if you look at the IP header, you have identification, flags like more fragment and don't fragment, and you have like fragment offset. Okay. Now, how does the identification field help you? So now, like we've said, right, you're sending packets from A to B. right? And I have to send basically packets. So I'm sending packets with 1500 MTU, right? Now I see that, okay, B cannot take that much packets. B can take MTU only, you can say 1200. So now consider only my first packet, for example. Okay, now let's take a better example. So let's reduce this MTU by 600. Okay, the MTU 600. So now I have to fragment my packet. So I'll fragment my packet into three packets, for example. First one is 1600, 600 that is allowed. Second one is again 600, so 1200. Now 300 is left. Now the third packet will be 300. So let me just mark it 600, 600, right? And then 300 because it's total 1500. So now each packet has to be sent from A to B. When it is sent in the buffer, B also has to identify and bring those packets together, club them and order in sequence so that it can get the data finally. So in order to get that data or process those packets, it has to be assembled properly. Now for them to be assembled, we use these three fields in the IP header. First is identification. Now for this particular for example, for this particular packet or this particular stream of packet, for example, we have a stream. Okay, we will identify a unique identification number. For example, identification number for this particular packet is example, it can be anything, right? 1111. So in all these packets, the identification number will be 1. Okay, let me use a different color so that it will be pretty easy for you to understand. Okay, so they have identification number of 1, 1, 1, 1. Now it has to be in order. So since this is the first packet, for example, it will have a fragment offset of 1, this will have of 2, this will have of 3. Now when it is assembled, it will be in 1, 2, and 3, but all of these will have the same identification number 1, 1, and 1. So for this particular stream, the packets are to be ordered like this because we can have multiple streams. Each stream will have a different identification number, but fragment offset for them again will be in a sequential order so that you can arrange those packets again. So this is how basically your identification fields help you in assembling the data back. Okay, and then process it later on. So these were the 5 interview questions that we discussed, right? And we also have another series for scenario-based interview questions. If you want to go ahead and you know, uh, basically read along those lines, I'm happy for you to do so. And if you have any other questions or any other topics that you would want me to discuss, we'll definitely do that as well. Right? I hope this was helpful. Thank you.